In this second video, we shall discuss with this parallel resonance circuit. So first of all, the question arises, what is this parallel resonance circuit? So here the three passive components such as inductance, capacitance and resistance. That means the series combinations of inductance and resistance is connected across the capacitor, and this combination is connected across the source of EMF. So this method of connecting an electrical circuit is called as parallel resonance circuit. Let E be the EMF of the that source, and that is equal to E naught into e raised to j omega t. In a parallel resonance circuit, the capacitor C is connected in parallel with the series combination of resistance and inductance coil L. The combination is connected across the AC source, and the applied voltage is a sinusoidal and is represented by that equation number 1. Then the complex impedance of the L branch means where the inductance is connected, that is Z1 is equal to R plus J into omega L, that is equation number 2. The complex impedance of the C branch is Z2 is equal to 1 over J omega C. Since Z1 and Z2 are connected in parallel, hence the total impedance that is given by 1 over Z, that is equal to 1 over Z1 plus 1 over Z2. Substitute the values of Z1 and Z2 from this equation number 2 and 3 and go on simplify. So 1 over Z, that is equal to 1 divided by R plus J omega L plus J omega C. So divide and multiply this equation by 1 divided by R minus J omega L and go on simplifying that one. So 1 over Z, that becomes R upon R square plus J omega R square plus omega L whole square plus J into that square rooted quantity, that is square bracket quantity omega C minus omega L, that divided by R square plus omega L whole raised to square. Take that as equation number 5. Now the current I is given by I is equal to E upon Z or E into 1 over Z. So 1 over Z is given by this equation number 5. Substitute that value here and you can arrive this equation, that is I is equal to E into, that is square bracket terms. So you define A cos theta as the first term of that square bracket term, and A sin theta as the second bracket, that is omega C minus omega L whole divided by R square plus into bracket omega L whole square. So on defining these two, take that as equation number 6 and 7. Substituting these values in the above equation, we have I is equal to E into bracket A cos theta plus J A into sin omega theta sin theta. A is common from these two terms, E into A into bracket cos theta plus J sin theta, or that is equal to E into A e raised to j theta. Therefore I value becomes, that is I is equal to E naught e raised to j omega t into A into e raised to j theta, or that is equal to A into E naught e raised to j into bracket omega t plus theta. That is given by equation number 8. So that means equation number 8, that gives the current in the circuit for a parallel LCR circuit. The phase difference that is given by, that is dividing equation number 7 by 6, that you are getting tan theta, and that tan theta is given by that equation. So that is therefore theta is equal to tan inverse of omega C minus into bracket omega L divided by R square plus omega L whole raised to square whole divided by R divided by into bracket R square plus omega L whole square. Take that as equation number 9. The amplitude of that current that we are getting, squaring and adding equation number 6 and 7, that we are getting equation number 10. Then you have to determine the expression for the admittance. So that is given by y is equal to, that is the reciprocal of the impedance is called as admittance. So that is equal to square root of a square, and that is equal to that substitute the values of a with a square rooted quantity. Okay, so that is given by that equation number 10, and simplifying that we are getting equation number 11. Next you have to define the condition for resonance. The condition for resonance in case of parallel resonance circuit is the admittance must be minimum. Therefore, from equation number 11 we have omega c r square plus omega cube L square c minus omega L. So that should be equal to 0. Or omega is common from all the terms, or you can write cr square plus omega square L square c minus L, that is equal to 0. On rearranging the terms and simplification, that we are getting omega square, that is equal to 1 over LC minus R square divided by L square. Or we have omega is equal to 2 pi fr at resonance. Therefore, that is equal to that square rooted quantity. Therefore, we can write fr is equal to 1 over 2 pi square root of 1 over LC minus R square by L square. So take that as equation number 12. So that equation number 12 is the expression for the resonant frequency in case of parallel resonant circuit. So we shall derive the condition for the resonance. If R is very small, it is too small, then R square divided by L square term is neglected. Hence equation number 12 reduces to Fr, that is equal to 1 over 2 pi square root of 1 over LC, which is same as that of the series resonant circuit. At resonance frequency, the admittance is minimum and the impedance is maximum. The conductance at resonance, that is equal to G is equal to R divided by R square plus omega square L square, that is using that equation number 11, we arrive at this equation. And the third important point is, for a parallel resonant circuit, the resonance is not possible if this R square by L square is greater than 1 over LC, because Fr becomes imaginary, which is in contrast with the series resonant circuit, where resonance can occur for all values of R in case of series resonant circuit. In other words, 1 over LC minus R square by L square, that should be real. Therefore, R square by L square should be less than 1 over LC, or R square, that should be less than L by C. That is, R should be less than square root of L by C, which is the required condition for parallel resonant circuit. So that means the resistance in the circuit should be always less than the square root of L divided by C. Then only we can get the resonant frequency Fr. The parallel resonant circuit, the quality factor is given by is the current magnification factor. What is this current magnification factor? The current magnification factor is the ratio of current through the capacitor to the total current in the circuit at resonance. Therefore, I can write I naught is equal to E naught upon Z, and that is equal to E naught RC upon L, that is Z value at resonance. The current through the capacitor branch is given by IC is equal to E naught upon XC, or E naught divided by 1 over omega C, or E naught into omega into C. Substitute the values of IC and I naught. Therefore, the magnification, current magnification M is equal to IC upon I naught, and that is equal to E naught omega C whole divided by E naught RC divided by L. So that becomes omega into L divided by R. So that is nothing but your quality factor Q. Therefore, at resonance, the parallel resonance circuit has the current magnification as that of the voltage magnification of the series resonance circuit, and is equal to the quality factor. The impedance at resonance, that is given by that equation Z is equal to R square plus omega square L square divided by R. The graph between current and frequency is shown in the figure. At resonance, the impedance is maximum and is given by this value, and the current is minimum. But at resonance, R square plus omega square L square, so that is equal to L by C. Therefore, Z is equal to L upon RC. Hence, the smaller the value of R, larger will be the impedance at resonance. If R is 0, the impedance of the circuit is infinity. The parallel resonance circuit is also called as rejector circuit, because the parallel resonance circuit rejects, that means it not allows the current at resonant frequency or natural frequency of the circuit, but it allows the current for other frequencies. Hence, it is called as rejector circuit or rejector filter circuit. So this is the comparison table between the series resonance circuit and parallel resonance circuit. In the first column, that we have given the specifications. The second, resonant series resonance circuit, and in the third column, parallel resonance circuit. The impedance factor, series minimum, parallel maximum. Current at resonance, in case of series resonance circuit maximum, in case of parallel resonance circuit it is minimum. The effective value of series resonance circuit, that is equal to R, whereas in case of parallel resonance circuit that is equal to L divided by CR. Resonant frequency FR, that is equal to 1 over 2 pi square root of LC. FR is equal to 1 over 2 pi square root of 1 over LC minus R square plus L square. It magnifies the voltage and is equal to the quality factor, whereas parallel resonance circuit magnifies the current and it is also equal to quality factor. The circuit is known as acceptor circuit, and here it is called as rejector circuit. The power factor is also unity in case of series, and in case of parallel resonance circuit that is also unity. So with this I conclude my lecture about this resonance and the parallel resonant circuit. In the next class we shall discuss the remaining topics of this transient circuit.